Well, hello there. I'm Venkatesh. Today's topic is about uh, ideal suffering. Before going to ideal suffering, let's recap the definitions of groups and related to it. Firstly, group. A non-empty set G with the binary operation star is said to be group if and only if it satisfies closure law, associative law, identity law, and inverse law. If these laws are satisfied, then that set, non-empty set, is said to be a group. In that group we have subgroups. uh, in that subgroup we get, after subgroup we get normal subgroup. So let's start with normal subgroup actually. mm, I have a small diagram which is very much easier to understand. A normal subgroup is a subgroup of n of group G that divides G into cosets. You can treat the cosets as elements in a new group, which is called as factor group. It is also called as quotient group. Uh, it it only happens when G and G inverse belongs to n, where for all G belongs to G and n belongs to n. So the formal definition of normal subgroup is said to be a subgroup of n of a group G is said to be normal subgroup G if and only if G and G inverse belongs to n for every G belongs to G and n belongs to n. In that normal subgroup, we get cosets as I mentioned a few minutes earlier. Now let's see what are cosets and what are its types. Now firstly we have right cosets. Uh, if we see what is right coset, let's jump on to the definition firstly. Let G be a group and H be a subgroup of G, then for any A belongs to G, the set HA, that is element of HA for all H belongs to H, is called right coset. Uh, if these are cosets, here we have taken HA. If we are multiplied to its right, if we operate to its right, we will get a right coset. So what is the left coset? Let G be a group and H be a subgroup of G, then forms any A belongs to G, forms A belongs to G, the set AH is AH for all H belongs to H is called as left coset of H. So all these in cosets normally we have right and left cosets. So I think this all from group to normal subgroup, right coset and left coset, we need these things to prove for ideal of a ring. How it is related, let's see now. So we have heard about com comprehensions. Now here we can see that ideal is to ring such that normal subgroup is to group. So as a group have a normal subgroup and rings has ideal. uh, I think I have not mentioned about rings anywhere. So let's see what is rings. A non-empty set R is said to be a ring with respect to two binary operations, that is addition and multiplication. It satisfies the following conditions that are our ring is an abelian group. R is closed under multiplication modulo multiplication, sorry, of for all A comma B belongs to R, A star B belongs to R. Multiplication is associative, whereas A comma B comma C belongs to R. uh, Multiplication is associative. A comma B comma C belongs to R for all A star BC is equal to AB star C. This is nothing but associative property. and R is also distributive. We can see left distributive, right distributive laws under multiplication condition. So we denote ring. So we denote ring under these two binary operation by R plus star, or simply by R. Let's write it clearly. Or simply by R. Then, as I mentioned earlier, we have ideals for normal subgroups. Now let's see what is left ideal and right ideal, because it is very convenient to explain after these types of ideal. It is easier to explain what is exactly ideal is. So let's take up first left ideal. Let R be a ring and U is a non-empty subset of R, then U is said to be left ideal. Generally we represent ideals in capital U. U is said to be a left ideal of R for all A comma B belongs to U. A minus B belongs to U, where A belongs to U and R belongs to R. R star A belongs to U. So if this condition is true, then that is said to be as a left ideal. Similarly, we can see that for a ring R and U is a non-empty non-empty subset of R, then U is said to be right ideal if A comma B belongs to U, A minus B belongs to U. This is same for left and right ideal. A belongs to U and R belongs to R. A star R belongs to U. You can see the difference, slight difference here. The multiplication varies. Here we have in left hand side, we have here in right hand side. The operation, sorry, to be precise, it's an operation, not multiplication. So combining these two, combining left ideal and right ideal, we can see what exactly the ideal is. So ideal is the let R be a ring and U be a non-empty subset of R, then U is said to be ideal. First condition, this is very much important. We are solving some of the problem using this condition. So firstly, A minus B belongs to U, for all A comma B belongs to U. A belongs to U, R belongs to R. If we operate RA, it is also belongs to U, and AR, it is also belongs to U. So by this left ideal and right ideal, we can say what exactly the ideal of R. So this combination of left ideal, right ideal, if it satisfy both the left ideal and right ideal properties, we can say that has that set as an ideal of a ring. For an example, even integer. Even integer forms an ideal in ring because the sum of even integer and product of that even integers is also an even. If we say that even integer and odd integers are so if we take any two integers, if we operate this property, we will get an ideal. To be precise, every one integer is an ideal. That's it, don't get confused. So let's recap what we have seen. From first, we saw groups and its property, closure law, associative law, identity law, inverse law, everything, and normal subgroup. What is normal subgroup, and cosets, types of cosets. Then comes ring and its properties, left ideal, right ideal, and their properties as well, and their properties. Okay, let's solve some of the problems. Before that, we have seen ideals, we can see improper ideal, proper ideal, simple ring. So every ring R has at least two ideals, which are now unit ideal and null ideal. So proper ideal, if we go to, we have dealt with improper ideal. If we go to proper ideal, ideal other than these two, that is unit ideal and null ideal, are non-trivial ideals of R. If we go to simple ring, a ring which has no proper ideal is called as a simple ring. So let's solve some of the problems now. So first problem, the set mx for all x belongs to integers where m is a positive integer is an ideal. Firstly, we are proving for ideal of a ring, that the ring is z plus star of integer. So here let's solve it first, then let's see what we get. Let's solve. Let us consider this as I. Let I is equal to mx and here let's take it as a belongs to I and b belongs to I. Then we know the property a minus b, so we are taking a and b here. Let's take a equal to mr and b equal to ms for some r belongs to z and s also belongs to z. Also let's apply the first property a minus b, that we get mr minus ms. So if we take m common here, r minus s we get, where therefore r minus s is will belongs to z, that is integer. Now for the first property is proved here. Let's take up for a second property, that is let's take r dash which belongs to z. So we have now, that is a r dash is equal to mr r dash, which is equal to r dash. We can write in this way, r dash belongs to I, where let's apply second property here, mr, where m also equals to r dash, which also belongs to I, where here r dash also belongs to an integer. By this we can say it as an ideal. Let's write it down. Let's write it down so that as we are proving it, we will get an clean idea of what we are doing. That is a belongs to I. We know we have taken that in earlier, and also b belongs to I. We have written here, but still I am writing so that it will be helpful in easier understanding. That is a minus b also belongs to I, the first property of an ideal, where I belongs to, sorry, a belongs to I and r dash belongs to z, that is an integer. A r dash also belongs to I. So hence by this too we can say that I is an ideal of z. I is an ideal. So we can say that a positive integer is an ideal in a ring of integer. That is we have done this. I think it is visible and clear. So thus we have proved that positive integer is an ideal. Now let's take up another problem. Now this sounds different. So the ring Z plus star is a subring of a ring Q plus star, basically integer and rational numbers, but it is not an ideal of Q plus star, because the product of rational number and integer may not be an integer. As the statement says, if the product of this integer and rational number, uh, I think it's visible. Hmm. The product of rational number and an integer is not an integer. That is, it doesn't satisfy the identity law. Let's prove it. Let's prove that with an example. Let's take, for example, for example, 3 is an integer. Let's write it on z. And 1 by, let's take 2 itself, quite famous one, is a rational number. So if we multiply, if we apply multiplication operation for these two, we can see it is 3 by 2, and it is not an integer. Yes, it is not an integer, and we can say that thus the product, it won't obey this property of an ideal, that is A belongs to I, R belongs to R, AR belongs to I. This property will not satisfy for this. Hence, this is not an ideal. This is an example for not ideal or non-ideal group, non-ideal ring. Sorry. Let's see another problem. Let's take up another problem. Uh, let's take a problem which satisfy only left ideal. Here I have taken a problem which only satisfy left ideal. That is, let's take up a set S of 2 cross 2 matrix of the form A0 B0, where A comma B belongs to integer, is a left ideal but not right ideal. As I mentioned, this is for only left ideal but not a right ideal in the ring R of all 2 cross 2 matrix over the set Z of an integer. Okay, let's take A as a 2 cross 2 matrix, that is A1 B1 0 0, and let's take up B has A2 B2 0 and 0. Let it be any two integer, any two element, of a set. Yes, where I will write here itself A1 A2 B1 B2 belongs to Z, that is integer. So if we apply first property of an ideal, that is A minus B, which implies A1 0 B1 0 minus, we are just subtracting these two, that's it, B2 0 0. We get A1 minus A2 B1 minus B2 0 0, which belongs to the set S. If you can ask how, I will write it down here itself, because A1 minus A2 belongs to Z, that is integer, B1 minus B2 belongs to Z. So the first property satisfy here. We want to show it is a left ideal. Again, let C equal to, we have taken A B C D, so we are taking as alpha gamma beta, be any elements of an ring R. Then if we apply left ideal, we get that is C equal to alpha beta B1 0. We are just now multiplying it. We get if we apply matrix multiplication, we get alpha A1 plus beta A1 plus B1. Correct enough. Correction here, sorry. We get 0 here. Let's close it here itself. It belongs to S. And yes, here we can say here it is left ideal where A1 and B1 comma belongs to integer and also belongs to Z. So here let's write it down. Let A also belongs to S and B also belongs to S, that is A minus B belongs to S, and C belongs to R, A belongs to S, that implies CA also belongs to S. CA also belongs to S, hence S is left ideal. As simple as it that. But here it is not right ideal. Let us show why it is not right ideal. I will write here itself. Let 1 0 1 0 as the matrix is, we take that as S as matrix, as this matrix. We are writing up this, and I could have written next page. Next page. Okay. Also belongs to R. If we apply right ideal to this, if we apply right ideal 1 0 1 0 1 1 0 1, we get 1 1 1 1, which does not belongs to set S. You can see this is not this, that is it is in some other form, and it is in some other form, hence it does not belongs to S, so it is not a right ideal. In the previous sum, we have proved for left ideal. If we want to prove for right ideal, in previous sum we have A0 B0. The matrix has A0 B0 where A comma B belongs to Z. If we take another matrix which is of same format, if we take another one, let's take as S is equal to A B 0 0. If we prove for this, we get it satisfy right ideal, but not left ideal. So this is all about right ideal and left ideal. Thank you for watching this video. Thanks a lot.